Good morning, guys. Today we're going to look at graphing quadratic functions. We're going to do that by transformations. There's actually two techniques we use for graphing quadratics. One is by transformations and one is by intercepts and calculating vertex. So we're going to look at transformations today. To be able to graph by transformations, we need to know what an original function, the parent function, looks like. So our parent function for the quadratics is just f of x equals x squared. This is the general shape. Vertex is at 0, 0. It goes through the points 1, 1 and negative 1, 1. And the actual shape is called a parabola. The graph of a quadratic function is called a parabola. Now, as you can see here, there are a number of transformations we can perform on this specific equation to change the shape. We can do shifts or translations. They can be called both things. And that's just where we move the graph left and right or up and down. We can do stretches or compressions, just like it sounds. We can stretch it or compress it both horizontally and vertically. And then we can do reflections, which is where we flip it over. Keep in mind, vertical reflection means we flip it across the x-axis. Horizontal reflection, we flip it across the y-axis. So the transformations just kind of do what you think they would do. If I'm going to shift something, I need to be adding the same amount onto every single point. So that's what we're going to do. If it's a horizontal shift, then it's going to impact just the x-coordinate. If it's a vertical shift, it's going to impact the it's going to impact the y-coordinate, so it's going to impact the entire function. Because remember what a function says, if I plug a value for x in, I get a y value out. So the x squared is the y's. X is the x coordinate, x squared is the y coordinates we get out. So just keep in mind with all your transformations, whatever direction we're impacting, that's the variable or coordinate we need to be impacting. So everything that's horizontal is going to impact the x. Everything that's vertical is going to impact the x squared, the entire function. So horizontal shift, we can see we're going to take that and we're going to subtract that distance from the x. And keep in mind with anything that's horizontal, we're going to do kind of the opposite of what we would intuitively think we should do. We're going to do the inverse operation of those. The reason being because the operation is on the same side as our variable. So if we were going to go through and solve and find out what x actually equaled, we'd have to move those operations to the other side. So if I wanted to increase x by the same number every single time, realistically I should be adding h to the other side of the equation. But when I've got it written as we write normal equations in y equals form, that all operations have to be written on the side of the x. So that's why we have to write it as the opposite of what it actually is, graphically speaking, visually. So any kind of horizontal shift, I'm going to do opposite. So if I'm going right 3 units, I'm going to put minus a positive 3. If I'm going left 3 units, I'm going to do minus a negative 3. So if you'll just remember, subtract your horizontal shifts, it'll take care of everything. The vertical shifts, since they're on the other side, y equals all of this stuff, we can just put exactly what they are. So vertical shift of k units is just add k on. If I'm going up 3, I add positive 3. If I'm going down 3, I add a negative 3. And that'll take care of all those. Stretch and compress is just like what you would think. If I'm going to make something twice as large, I've got to multiply all my values by 2. So that's where the multiplications come into our transformations. Again, all the x's, we want to do the inverse operation. So the inverse of multiplying is multiplying by reciprocal. So if I see a number times c, it's a horizontal, a number times x, it's a horizontal stretch or compress by a factor of its reciprocal. So if I'm going to make if I want to make something twice as wide, I've got to multiply it by the reciprocal of 2. So I've got to multiply it by 1/2. If I want to make something half as small or half as narrow, then I'm going to multiply by the reciprocal of a half, which is 2. So just keeping in mind we're doing the inverse operation for all of our horizontal transformations. And the y's, we just take them as they are. If I've got a number on the outside of the x squared, then we know that that's a vertical stretch by a factor of c. So if I'll make something twice as tall, I just multiply it by 2. Something half as tall, okay, so we're going to compress it by a half, then we just multiply it by a half. So the y's, we get to take them as they are. The x's, we have to do that inverse operation. Okay? Keep saying that because it's very, very important. That would make the distinction between the two. Also remembering, vertical is up and down, that's the y's. Horizontal is left and right, that's the x's. And then finally, the reflections, just make them opposite. That's what reflections are. Take all your positive points, turn them into negative points. Take all your negative points, turn them into positive points. Well, we do that by multiplying by -1. So technically, where it says here we're multiplying the x by negative to get a horizontal reflection, really we're multiplying by the reciprocal of -1, because we see right here, anything we do to x, we have to do the inverse. But the reciprocal of -1 is still -1. So we just leave reflections as they are. We don't really have to do much manipulating and tweaking with them. So if I want a horizontal reflection, I multiply just the x by the negative. If I want vertical reflection, I multiply the entire x squared by the negative. Now keep in mind here, if I take negative and put it with just the x, when I square that, negative x times negative x is positive x squared, which intuitively should make sense. Because if I take this graph right here and I reflect it horizontally, I'm going to get the exact same picture. So if I take this and I flip it around horizontally, you still get the same x squared picture. So horizontal reflections, when we're centered at the y-axis, as this one is, they're not going to show up. And there's a reason, for the reason we just stated. But anytime we're not centered at the y-axis, then they would show up, because when we say horizontal reflection, we're talking about reflecting it across the x-axis or across the y-axis. So keep those things in mind. Sometimes they don't say the word reflection. Sometimes it's posed to you as reflect across the x-axis or reflect across the y-axis. So it just, if you want to write that down, horizontal reflection is across the y-axis. A vertical reflection is across the x-axis. And that's sometimes trips people up, because you think, oh, across the y is vertical. No, the y-axis is right here, so if I'm going across the y-axis, I have to move horizontally. The x-axis is right here, so if I'm going across the x-axis, then I'm going to have to move vertically. So across the y is horizontal, across the x is vertical. So make sure you pick up on that and just pay attention to the detail of it. Give me a second, we'll get a couple examples up here to take a look at these transformations. So here we have a couple of examples. I want you to describe each transformation, then we're going to graph. So transformations first. Remember, transformations, anything that's multiplied, added, or negated. That's what we're looking for. So first thing I see is this times 2 out here. Now remember, if it's attacking just the x, then we look at it as a horizontal transformation. If it's attacking the x squared, then we want to look at it as a vertical transformation. Well, what we can see is this is not in parentheses with that x. It's attacking or attaching itself to the squared portion, the x squared. So that makes it a vertical transformation. And we can go through and just kind of label each one of them. This +1 is in parentheses with the x, so it's working on just the x coordinates, so that one's horizontal. The -4 is on the outside of the parentheses, so it's working on the entire function, so that makes it vertical. Okay, what's this operation? It's 2 times the parentheses, so that's going to make it a stretch or compress 2 times. So that's bigger than 1, so it makes it a stretch. It's a compress if it's between 0 and 1. Horizontal, we're adding on, so that's a shift. This vertical, we are subtracting a number, so that is also a shift. Or you could write vertical translation or horizontal translation. Those are okay. Shift and translation are interchangeable. Now how much? Vertical stretch by a factor of 2. This x, it's a horizontal shift. And remember, all horizontal shifts have to be x minus. So that's minus a negative 1. So that's a horizontal shift left 1. We get a little bit of 1. We'll just space it out. So left 1. Fancy one. Vertical shift, again, it's supposed to be addition, so it's plus a negative 4, so that's going to be down 4. So those are our transformations. We have a vertical stretch by a factor of 2, we have a horizontal shift, left 1, and we have a vertical shift, down 4. So if we go through and graph that, instead of starting at 0, 0 like we normally do, you always want to get your shifts in first. I got to know where my new starting point is. I'm going to go left 1. I'm going to go down 4. So let me redraw this real quick. So left 1, down 1, 2, 3, 4. That's my new vertex. Okay, and here's my stretch. Now, typically, we know that we're at, if we're doing the parent function, we're at 0, 0, we go 1 and negative 1. Okay? I just like to call that the one-to-one box. And the reason is because if I plug 1 in, I get 1 out. Plug negative 1 in, I get a positive 1 out of the x squared function. Okay? The f of x equals x squared function. And all your functions are going to work like that. Your transformations, your parent functions, you plug a 1 in or a negative 1 in, you're going to get 1 or negative 1 out. Well, what's changing? We're going to be plugging a 1 in because we didn't change how far left and right we move. But when I plug a 1 in, I'm getting a stretch of 2. So instead of it being 1 in, 1 out, it's now 1 in. So 1 in for x, 2 out. And the same thing going the other way. Negative 1 in, I'll get a 2 out. So that's how we demonstrate the stretches. If the stretch had been on the x, the y's wouldn't have changed, so we'd still have our 1-to-1 on the y's, but we'd be going over whatever our x stretch is. Instead of it being 1 in, it might be 10 in. So I'd go over 10, but I'd still only go up 1. So we then connect the dots. Don't worry too much about the details past that. We'll work on those when we get into calculating some of these points. Like to label the vertex always, so -1, -4. And that's our graph. And we can see that it is twice as tall. It got stretched where the other one was over 1, up 1. Now we're over 1, up 2. So we're twice as tall as what we were before. We've moved it left 1 and down 4. Okay, so that's how you want to go through. Describe each transformation within the function and then graph it. You do not have to show this original function. I was just trying to show you how we changed from the original down to here. All I really need to see from you is that transformed function. All right, if you will pause the video here, take a couple minutes, try to work through this example on your own, describing each transformation and then graphing it, and I will wait right here, guys. All right, let's, hopefully you were able to get that solution or this graph. Let's see how you did. So going through, I see this negative sign on the outside of the parentheses. That tells me it's vertical. I see a times 2 on the inside of the parentheses. That tells me that one's horizontal. I see this 3 on the outside. That tells me that one's vertical. Negative we know is a reflection. Multiplication we know is a stretch or compress. We'll kind of decide that one in a second. Vertical, and we're adding it, so we know that that one is a shift or translation, if you want to call it a translation. All right, translation up here so we can have one that says that. Okay. All right, so the vertical reflection, that one's already done. Horizontal stretch by a factor of how much? Well, remember, we're always working off reciprocal. The formula was 1 over the stretch times x. So the reciprocal of 2 would have to be 1/2 times x, or 1 over 1/2 times x. So our stretch, because we're supposed to be 1 over c times x, 1 over c, our c has got to be 1/2. So as we can see right there, it's not a stretch, it's actually a compress. Because we're compressing it by 1/2. So we're going to have a horizontal compression by a factor of 1/2, and then vertical translation plus a positive 3, so that should be up 3 units. And then we go through and graph. Okay. Let's see. You always want to do your shifts first, your translations first, so we're going to go up 3 units. 1, 2, 3 units. We're not shifting it left or right or all, so that's my vertex. Now we want to do our stretch or compress by horizontal factor of 1/2. Let me make this graph a little bit bigger so you'll be able to see what's going on. Okay. That'll give us a little better picture. So instead of going left and right 1 as we did in the original, or as we did in this one where we didn't have a horizontal stretch, now we're going to go left and right 1/2. So if there's a 1, 1/2 will be right in here. Now the vertical component, the vertical stretch didn't change. There's still a 1 out here, but actually since it's a negative 1, instead of going left and right 1 and up 2 like we did here, left and right 1, up 2, reading it almost like a slope, we're going to go left and right 1/2, and then we're going to go down 1. And so that builds our vertical reflection into the actual transformation process, into that. I mean, it's not a slope, but if you want to kind of consider it like one. So whatever the coefficient of x is, the reciprocal of that is how far over you're going to go, and then whatever the number on the outside of your parentheses, on the outside of your x squared parent function, then you're going to, that's going to be your vertical component. That's how far up or down you're going to move. And again, if this x had been negative, we'd have that horizontal translation, but we'll, that one is what it is. If we're centered at 0, then you're just going to flip it. So if you're centered at the y-axis, you just flip it and it doesn't change anything. But if we'd have been over here and had a horizontal reflection, we'd have then had to flip it over here. So we'll have some of those come up in our homework, and we can talk about them then, or in our classwork rather. All right, so that's how we describe the transformations and then actually build a graph using those transformations. Give me a couple seconds and I'll have another way we can look at these problems for you. Okay guys, so now I want to talk to you about something that we call vertex form. As you can see here, this vertex form, f of x equals a times the quantity x minus h squared plus k. All this is our transformation form. Same stuff we were working with before, but we're giving it a specific name And we call it vertex form because you can explicitly see where the vertex is. Vertex of the parent function x squared is at 0, 0. Well, this is telling me how far left and right or up and down to move that vertex. So those are going to give me my vertex coordinates. The A, as we know from before, it's being multiplied out front, so it's going to tell me what my vertical stretch or reflection is. So we get a lot of observations that we make just by looking at the equation. We know where the vertex is. We know really what direction the graph is pointing. Because if A is positive, then there is no vertical reflection, so the graph will open upward. If A is negative, however, then we have that vertical reflection, and so the graph is going to open downward. So what I want us to look at is being able to take something that's in what we call standard form, like we have here, and write it in vertex form. So ask yourself, what's the relationship between this vertex form and this standard form? Okay, well the vertex form we can see only has one x in it, and the standard form has multiple x's. It has a quadratic term with an x and a linear term with an x. Well, this just has the one quadratic component. So if we're going to get it from this form to this form, we need to find a way to write it as a linear binomial that's being squared instead of a linear component and a quadratic component, or terms. So we've used a technique before where we move from this form to this form, which should be familiar to us, and that technique is called completing the square. So to get from standard form into vertex form, there's actually two techniques. I'll show you one of them in this lecture. The next lecture where we talk about vertices and intercepts, or vertex and intercepts graphing, then I'll show you the other technique for being able to get it into vertex form. But right now, let's just use completing the square. So completing the square, we know the first step is get rid of all your constant to the other side. Well, we're not solving, so I don't want to get rid of it to the other side. I just want to set it to the side. So we're just going to move it over here out of the way. So I've got my x squared minus 6x, and this is the part where I'm going to try to get that perfect square trinomial. And if you need a reminder on completing the square, just go back and watch the completing the square lecture. So I've set that 4 off to the side over there. Okay. Now remember, we want to add b over 2 squared into our quadratic trinomial to make it a perfect square trinomial. So I want to put my plus b over 2 squared into this quadratic. Well, what was our b? X squared minus 6x. B is negative 6 over 2 quantity squared. So this is going to give me my perfect square trinomial. Well, where we have to balance out is before, where we added b over 2 squared to one side of the equal sign, one side of the equation, we'd add b over 2 squared to the other side of the equation. Well, we're not touching the other side. It's just your g of x. So we've got to balance the equation on the same side. So we're going to take this b over 2 squared that we added here inside our quadratic trinomial and subtract it over here. So we increased this portion of the right side of our equation by b over 2 squared. So we've got to decrease this portion of the same right side to keep the equation balanced. It's kind of like we're borrowing from this constant we have out here, however much we're going to need to make that perfect square trinomial. So we're just going to subtract out of this 4 whatever we happen to need to let the rest of this stuff be able to factor, and that keeps us balanced. We go on through, we know we have x squared minus 6x plus 9, plus 4 minus 9, say plus 9 minus 9, still that's 0 for the whole equation, which we haven't changed the value of the right side, we're just changing the way it looks. And we get x minus 3 times x minus 3 minus 5. So I get x minus 3 quantity squared minus 5. That is my vertex form of that function. So we can see a couple things. I can see that my vertex is at 3, negative 5. Remember, opposite the x coordinate, take the y coordinate as it is. So vertex is at 3 and negative 5. We have a positive lead coefficient, so this graph is going to go open upward, and we have no horizontal stretch. So it'd be real easy to graph that one. once we do a couple steps of completing the square and getting it into vertex form. Give me a second, I'll get 2 more examples up here for you guys to try by yourselves. Here you go, guys. There's 2 examples up here where you will take each of these scenarios and write each of those functions in vertex form. So there's one similar to what we did a minute ago. A little bit of a difference, so kind of remember all those steps for completing the square. And then this one here where I give you 2 points, and I want you to be able to use them to come up with the function in vertex form. So you take a couple minutes, pause the video, work these 2 examples out, and I will wait right here, guys. Okay, let's see what y'all came up with. So on this first one here, we want to go through and do completing the square. So I've got my 2x squared plus 4x. We're going to take it, kind of group it together, and we're going to set that minus 2 off to the side. So that was always your first step of completing the square. Move your constant to the other side, or in this case, just set it to the side. Second step was get a lead coefficient of 1. I've got to dump this 2 first. So before, where we divided both sides of the equation by that lead coefficient, now I'm just going to divide this one component. I'm going to factor that lead coefficient out. So if I factor the 2 out, so if I just factor a 2 out of each term, I'm left with x squared plus 2x. And then there's my minus 2. Now we're ready to add the b over 2 squared into our problem. So plus b, which is 2 over 2 squared. So that's going to give me 2 times x squared plus 2x plus 1, which we know is a perfect square trinomial, minus 2 minus the b over 2 squared out here. So b over 2 squared, we got added inside parentheses here, so b over 2 squared has got to be subtracted on the outside of the parentheses. But there's something else we've got to do on this one, and it comes back to this 2. If we've increased this set of parentheses by b over 2 squared, we've increased the side, this whole side, by 2 times that. Because this is 2 times everything in the parentheses. So anytime you've got a factor, a lead coefficient that you divided out, that you factored out, you've got to remember that when you subtract your b over 2 squared from outside the parentheses, you're actually subtracting that lead coefficient times the b over 2 squared. So this 2 is the reason we've got to have that 2 right there. And we've got a lot of 2's in the problem right here. But this 2 is the reason that 2 is there. Now we go through and finish. We know that that is going to be x plus 1 times x plus 1, which is x plus 1 quantity squared. We've got 2 times 1 is 2, negative 2 is negative 4. So we get this function right here. Hope some of you were able to get that. Remember that factoring of the common factor, factoring of the lead coefficient out, and then remembering to bring it into account when we balance our equations. So if we were looking at this one, we could describe this function pretty easily. Vertex is at negative 1, negative 4, because remember we're taking opposite of that x transformation there, or inverse of it. We can see that we don't have any horizontal or vertical reflections. It's still going to point up, but it does have a vertical stretch of 2. So we get all the information we need about this function from that equation right there. We can graph any of it. Well, let's look at number 3 over here. Number 3 is a little bit different in that we don't have the equation, but they're giving us the vertex, which is very important. So we can treat this almost like you can when you're working linear equations. They give you a point and they give you the slope, and plug it into point-slope form. Well, when we have a vertex for a quadratic, we get to plug it into vertex form. So if I've got y equals a times x minus h quantity squared plus k, that's my vertex form, correct? Because f of x just means y. F of x is all values that come out of a specific relationship when you plug x into it, which is your y, which is your range values. So if I've got my vertex, I've got my h and k, so I need that The only thing else I really need in this is my a. Because I have x minus 1 quantity squared plus 2. So if I figure out a, then I can write my whole function in. Okay, because this is what we're trying to get to, right? Or g of x or h of x or whatever you want it to happen to be. So I'm trying to get to this, but I don't know a. So what I can do is take h and k and let this be x and y, because that's an x and a y for this specific relationship. And we just go in and solve. So y is negative 5. A is what we're looking for at the moment. X is 2. The x is 2. H is 1, quantity squared. K is 2. So I just took all these values and plugged them into my formula. H was 1, K was 2, X was 2, Y was 5. So we just substituted all those in. And now we can figure out what A is. So go through, do the arithmetic. Negative 5 equals A times 1 squared plus 2. Well, 1 squared is 1 times A is A. So A plus 2 equals negative 5. So move your 2. So A equals negative 7. Put that into your vertex form. So negative 7 times x minus 1 quantity squared plus 2. And instead of having just one point and the vertex, we now have the equation for all points and the vertex for that specific quadratic. So again, there are other techniques to get from standard form into vertex form, or to get from a vertex and a point into your vertex form. We're going to look at those in the next lecture. But this is how you can work these types of problems. Just relating it all back together with your transformations and how the different pieces fit together within that vertex form. That's graphing quadratics using transformations. And if I don't see you in class before your next lecture, then I'll see you in the next lecture.